Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in. Okay, explain why a gas can be compressed, but solids and liquids cannot. So what are the key differences between gases that would set them apart from both solids and liquids? It's how far apart the gas particles are, and the fact that they've completely broken their bonds between different particles. So that basically means that in a way that we can't for solids and liquids, because those are already quite tightly packed, we can actually compress gas particles and bring them closer together. Okay, in what ways are gases and liquids different from solids? So firstly, I'm looking for properties that are common with gases and liquids and not for solids. The first one is the kind of pattern that they're in. Remember, your solids are in a regular fixed pattern, whereas your liquids and your gases, we talk about liquids being irregular, okay, they're not a regular pattern, and gas particles being completely random in their position. And also, they are obviously free to move around. Your liquid particles can move over each other, and your gas particles can move around a lot. Also, we could talk about the fact that they both have more potential energy than solids. Remember, your potential energy is increased as you begin to break the bonds between the particles. So your solids have extremely strong bonds between particles, slightly weaker for your liquids to allow them to move over each other, and then weak for your gases where they can actually move around. Okay, let's have a go at some density calculations. We have what is the density of a cube with a mass 600 grams, a length 0.2 meters, and I want it in grams per centimeter cubed and then kilograms per meter cubed as well. So I'm going to look at my grams per centimeters cubed first, and as always I need to think, what is my equation for density? So my equation is density, I've given it that little symbol rho there, is mass divided by volume. So what is our mass in the question? Well, it is 600 grams. Now, because at the minute I'm looking for a density in grams per centimetre cubed, I can leave my mass in grams because that is matching the units of my density. And then volume, well, I need to figure that out from my information in the question. So what do I have? I have the length of my cube in my question. And I've decided I can't leave that as 0.2 meters. I first need to convert it into centimeters. And if you can spot why, that is because I'm gonna need my volume to be in centimeters cubed so that it matches the volume in that density unit that's been given to me. So 0.2 meters times by 100 to get it into centimeters, 20 centimeters. Now I've converted my length, I can figure out my volume in centimeters cubed. It's important that you do convert at this point here. So get those lengths into the correct unit before trying to figure out the volume. It's a cube, so I'm multiplying all the three sides together and they're all the same length. So 20 times 20 times 20 is 8,000 centimeters cubed. Now I do my equation. Density is mass over volume. 600, my mass in grams, divided by 8,000, my volume in centimeters cubed, equals 0.075 grams per centimeter cubed. Okay, now to do the second part, which was actually to do a similar thing, work out the density of this cube, but this time in kilograms per meter cubed. So I've got my exact same equation as before. This time I need my mass to be in kilograms so that it matches that unit of my density. So 600 grams divided by 1,000 gives me 0.6 kilograms, And now I just need to figure out my volume. This time, the length of my cube I'll leave in meters because I want my volume to be in meters cubed from my density unit. So volume of a cube, multiplying those three sides together, 0.2 times 0.2 times 0.2 gives me 8 times 10 to the minus 3 meters cubed. Okay, then following through with my formula, mass 0.6 divided by 8 times 10 to the minus 3 gives me 75 kilogram per meter cubed. Okay, question on energy changes. Explain what happens to the particles of water in a kettle throughout the boiling process. Okay, so in order to boil my water in a kettle, first I take my water at whatever temperature it is, probably like room temperature, maybe a bit colder from your tap, and I need to increase that temperature to 100 degrees. Now, you need to remember when you're increasing the temperature of something, what you are doing is allowing those particles to move around quicker. The energy that you are giving to them makes them have a higher average kinetic energy. Okay, so that's the key here. Your temperature is directly related to how quickly those particles are moving around. So the particles in your liquid begin to move around a bit quicker, and then as I actually start to boil this water and it changes state from liquid to a gas, that is when I am using my energy to break those bonds between my liquid particles so that the particles can move further apart. That would be increasing the potential energy of my substance. By breaking those bonds, you increase the potential energy of your water so that it becomes a gas. And key thing to remember here that people often forget is this process actually happens at a constant temperature. So that implies your particles aren't actually moving around quicker during this process. All of that energy is being used to break the bonds between your particles. Okay, some specific heat capacity calculation. So how much energy is needed to raise the temperature of milk of mass 300 grams from 10 degrees to 25 degrees, and it gives me the specific heat capacity of milk. Okay, so first things first, what is my equation? Q is equal to MC delta T, energy, make cup of tea, MC delta T. That's how I remember that that's my equation. C here, it's been given to me in the question, 4,200 joules per kilogram degrees C. Now, I need my mass, M. I've written it as not 300 grams, but divided that by 1,000 and written 0.3 kilograms. Again, I need to look at my units that they've given me for my specific heat capacity C. And you can see it's joules per kilogram degrees C. So if I'm going to put a mass into this equation, it better be in kilograms. Then my change in temperature, that is my final temperature minus my initial temperature. So in this question, 25 degrees minus 10 gives me a change in temperature of 15 degrees. So remember that delta T, remember that's quite important. It's actually your change in temperature of your substance. So I can plug it all in now. Energy is mass 0.3 times C 4,200 times change in T 15 gives me 8,900 joules of energy. Okay, now it's going to ask me if instead I had this mass of milk of 1.5 kilograms and it has an initial temperature of 10 degrees and I give it 300,000 joules of energy, what is the final temperature of that milk going to be? Since this is a question about temperature, I know my equation is still Q is MC delta T. And what information do I have in my question? Well, I have my mass of 1.5 and I have my C from the question before. Remember C, your specific heat capacity, just depends on the material. So since this is still milk, my C is the same, 4,200, and I have my energy Q of 300,000 joules. I'm trying to find first my change in temperature, and then I can use that to find my final temperature. So let's do that bit first. Let's plug everything into my equation. Q is MC delta T, 300,000 is 1.5 times 4,200 times change in T. Now I'm going to simplify that right hand side, so I'm just going to leave 300,000 equals 1.5 times 4,200, which is 6,300 times delta T. Now I'm going to divide both sides by 6,300, so 300,000 divided by 6,300 gives me 48, and that is my change in temperature. Now, that wasn't actually my question. My question wasn't the change in temperature, it was what's the final temperature of this milk. Remember, your change in temperature is your final temperature minus your initial temperature, and here my change in temperature 48 is the final minus, it told me in the question the initial temperature was 10 degrees. So if I add 10 to both sides, my final temperature is 58 degrees C. Okay, now on to specific latent heat. How much energy is needed to boil 50 kilograms of water, and how does this compare to the energy required to melt ice? Suggest why. So your energy, Q, is mass times L. So in order to boil water, let's do that one first. We have our mass being 50 kilograms, and our L, well, because it's boiling, it's a specific latent heat of vaporization, the idea of vapor there going from liquid to gas. So that is 2,260,000 joules per kilogram. So your energy is 50 multiplied by that gives you 113 million joules. Okay, next, to melt ice, we have the same idea, 50, but this time it's specific latent heat of fusion, the idea of fusing things together, so that's between solids and liquids, and we have 50, therefore your mass times L, 334,000, and that gives us 16,700,000 joules. So how do they compare to each other? Well, clearly it uses more energy to boil the same amount of water than it does to just melt that amount. And why do you think that could be? Perhaps it's harder, and therefore you need more energy to break the bonds completely between a liquid and a gas than it is to just weaken those bonds from a solid into a liquid state. Okay, so a slightly more tricky question, which is, okay, how much energy is therefore required to take 50 kilograms of solid milk at 0 degrees and boil it completely? So we're going to need the information that we had in a second from the page before, where we were looking at how much energy to melt that amount of milk and to boil that amount of milk. So we have this idea that in order to be able to do this, we're going to need to melt the milk first, but then that is going to be at 0 degrees. We're then going to need to raise the milk's temperature from 0 degrees to 100 degrees. And once we've done that, we can then boil that milk at 100 degrees. So how are we going to do this? We are going to find the amount of energy first required to change that milk's temperature once it is melted from 0 degrees to 100 degrees. So Q equals MC delta T, therefore the energy required is going to be the mass of it, the milk, 50 times 4,200. We've put that as our C here. We're kind of assuming for this question that milk acts very similarly to water, which is exactly why the change in temperature needs to be 100 degrees minus 0 degrees, its initial temperature, because we're going to say that it's going to boil once it's reached 100 degrees. So if I multiply those things together, I get 21 million joules. And now I need to find the total energy. So from the slide before, it was 113 million joules to boil it. And now I've just found it was 21 million joules to raise the temperature between 0 and 100. And I need the energy to have melted the milk in the first place too, which again from the other side was 60,700,000. So if I add them all together, In total, it was 150.7 million joules to melt it, then raise its temperature, then boil that milk. Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not? Firstly, your units for the section. So density can either be grams per centimetre cubed or kilogram per metre cubed. And what I'm saying here is really when you're trying to figure out the density of something, you need to know, do you need your mass in grams and your volume in centimetres cubed, or kilograms and metres cubed? And you need to check the density units match the units of the mass and volume that you use to calculate the density. Same for your specific heat capacity C. Is it joules per kilogram degrees C or joules per gram degrees C? So check that as well, that if it is joules per gram degrees C, the mass you're plugging into your equation is in grams, and if it's joules per kilogram degrees C, that your mass you're plugging in is in kilograms. And on the point of units, if you do have to find a volume first before you find your density, make sure that if you're trying to find your volume in meters cubed and they've given you a length in centimeters, convert the length first. Convert from centimeters to meters or meters to centimeters before calculating your volume. Don't try and convert from centimeters cubed to meters cubed, because you're likely to use the wrong conversion rate, to use divided by 100, and that's not true because it's each of those lengths which is divided by 100. Okay, no change in temperature when changing state. That's just something to remember, but it's something that pupils often forget. And it's a bit counterintuitive that you're heating something, you're giving heat to something. Really, that's just energy, and your particles are using them to break the bonds, not to move around quicker. So actually, you're not increasing the temperature of your particles when you are changing state. Finally, I always get, how do I know whether I'm using MC delta T or ML? Get really confused. They're to do with two different things. MC delta T is when they are talking about something raising its temperature. So if ever you see the idea of temperature being increased in a question, that's a clue you need to use MC delta T. Whereas ML is all about the energy to change state. So it's boiling, it's melting, it's freezing, it's condensing. That's a cue where you need to use ML, your specific latent heat. Sometimes, like that last question we did, you might need to use them together because you are melting something and then raising its temperature, for example. So that's how they can make it really hard. But break it down into its separate bits. Each phase, take it separately. Melt it first, then change temperature, MC delta Q. Then if it wants to be boiled as well, then go back to ML again, and so on and so forth.